Hello, welcome to the course Electronic System Design. Last lecture we discussed about the schematic design where we use KiCad software and we create a schematic using some symbols, very small schematic we prepare, and we saw various steps. How do we take the symbol from a library, put it together in the schematic sheet, connect them together using a wire, then we need a ground plane and the supply plane. We saw that we can label a net by the net label command. There is also very good option that if we have large circuit and we want to connect so many components to each other, then it, because of if we run so many wires, then the schematic visually looks very difficult to solve. However, if we give the same name to that node, to that wire, they are assumed connected. So, it increase the visibility. However, this is also a not so good option, because if we mistakenly connect the wire by the names, and if a unwanted net is given the same name which we do not want it to connect, it is very difficult to find out where that exactly the error has come in the schematic. So, we should use that option very carefully. Then we saw that this schematic we need to run a ERC or electrical rule check, which is a set of rules. These rules are standard rules which you can go into ERC dialog box and find out what are all the rules. So, these are general rules which prevent certain errors only in the schematic. This is not exhaustive list of all the rules that once ERC is checked, there is no error in the can be in the schematic. It can be there, but most frequent errors are generally flagged by ERC. Then it is up to us, we want to accept that error. We have sometime we want intentional connection of two wires which is flagged by ERC. So, that time we ignore that error, or if it is a mistaken one, that we have to take a call whether we should accept this error or not. Similarly, warnings we need to check very carefully if that is acceptable to us or not. So, once the ERC is clean, we go to the bill of material. We import all the bill of materials, whatever we want to purchase from the marketplace. We place the order and we get all the components. So, that once we design the PCB, we already have the components to put in. So, we saw the schematic design, the complete schematic design. Then the next step is to create the PCB for that schematic, PCB or the board, in short we call it PCB or the board. So, that board preparation step by step procedure we are going to look today. So, let us go to the KiCad software again. So, to start the PCB editor, we again go back to the main window of software, which looks something like this. So, today we are designing the circuit board. So, when the schematic is completed, we go back to project window and open the PCB editor. So we go back to project window, which is this window, and now open the PCB editor. So this is the button for PCB editor, or there are two files available here. One is for the schematic and one is for the board. So that board file we can double click on it and make it open. So either way we can do it by PCB editor as well, or we can go by the board file. So once we want to open this board file, now the very first step which the software need to know is the default setup, what we want to have, for example, the size of the board, the orientation of the board, so and certain like title or anything we want to give. So first step is to prepare the board setup and stack up. So the first step is this board setup. Board setup is nothing but we are telling the software that what is the size going to be for our PCB. For example, here we have specified the size for our board, which is 8.5 by 11 inch, and the orientation is landscape. And then we have certain fields for our information. So these are just for the information. We can write anything here that has nothing to do with the electrical functionality of designed PCB. This is just for our information. Here we can specify the version of PCB. If we have multiple PCBs or multiple iterations in the same PCB, that time we can use this option for the revision. And this is the preview window which shows the preview of our PCB sheet. This is currently in the landscape mode. If it is portrait, then it will come like this. So this is the dialog box for board setup. So before designing the board, set the page size and add information to the title block. So this is our title block where we can add all the necessary information we want to add. This we can access using file and then page settings. So we go to file and then we go to page settings to access this dialog box. So this is the board setup where we are specifying size and orientation for our board sheet. The next is the board stack up. So we are continuing the previous topic, which is board setup and stack up. So this is the step which is very important step here, that we are specifying in the PCB that what will be the layers we will be using and what are all their parameters. For example, we will be using a copper layer, and the copper layer will have a thickness of 0.035 mm. We have a substrate for PCB. For example, FR4 substrate we want to use for manufacturing the PCB, and the thickness of that PCB material is going to be 1.51 millimeter. You can change the readings as per your desired ones or whatever is offered by the manufacturer. So generally these manufacturers specify the dielectric thickness, which are standard quantized thickness. You can only choose from those available thicknesses only. You cannot change much here, but of course you can choose whatever is available from the manufacturer. So if it is 1.5 or even half of this or even double of this, so based on that we can choose this material thickness, the copper, or we call it sometime the cladding, the thickness of copper material on the top. This is FCU, means the front layer of copper. This is BCU, which is the back layer of copper, and both have thickness of 0.035 mm. This is the thickness of copper which is pasted on both sides of FR4 substrate. FR4 substrate has 1.51. So this is the dialog box which we should open before this starting on the board design. We need to specify all the parameters here, whatever is crucial for our design: front layer, dielectric, back layer. Sometimes we want silk screen as well, the top silk screen. We have top solder mask, top solder paste, and so on. We have multiple layers here, and we can specify the thicknesses. If we are going for 2-layer copper, 2-layer PCB, we can in fact increase the number of layers. For example, we are going to 4-layer PCBs, then we just click on it and we can choose 4 layers. Then we can have multiple option for dielectric 1 as well as dielectric 2 as well as dielectric 3 and so on. So all these parameters, whatever we are going to use in our PCB design, all these need to be specified in board stack up step. So this is the very important settings in the software. It tells us what copper and dielectric layers the PCB will have. And their thickness. As we can see from the calculator app, the performance of microstrip lines at high frequencies, that depends on the thickness as well of these dielectric. So we need to carefully choose our PCB material if we are going for very high speed PCB design or RF PCB design. So, however, for the slow speed PCB, this thickness of dielectric plays very little role, and it does not cause any performance issue for low speed designs. In this step itself, we can specify the design rules as well. So there are design rule options available here, where we can click and set all these design rules. So if we click on these design rules, we have so many rules which we can specify. So we go to design rules and then constraints. The settings on this page specify the overriding design rules. For example, if we click on constraints, the default design rules will be visible. For example, minimum track width here, which is by default taken by software, is 0.2 mm. However, if we want the wider traces for all of our design, then we can choose 0.3 or 0.4. Then when we will draw the track, automatically a minimum width of 0.4 will come. Of course, that we can increase during the design process, but these are the default values which we can change here. Settings on this page specify the overriding design rules for everything in the board design. Then we go to net classes, which is again one important dialog box. So this dialog box specifies the values, whatever is the default will be taken by software. For example, for the clearance, software will use 0.2 mm. For track width, there will be a 0.25 mm value will be taken. Via size will be 0.8 mm, which is by default. Whenever we will choose a via in our PCB, by default it will come 0.8. Of course, we can change it here, and that will be reflected in the PCB. So, this dialog box is a set of design rules associated with a specific group of nets. The net class is a set of design rules associated with a specific group of nets. In fact, this page lists the design rule for each net class This page lists the design rules for each net class in the design and allows assigning nets to each net class. So, these are the certain set of rules which we need to tell the software before we jump to the PCB design. These will be the default design rules taken up by the software. The next step now is creating the PCB from our schematic. So, in the last lecture we have created a sample PCB or sample schematic, and now we want to start creating the PCB for that. For that we import the changes from schematic. In this step we are opening the tools in the software. We go to the tools and update PCB from schematic. Here we are telling the software that we want to import the footprints, whatever we are using the devices in the schematic, we want to import the associated footprint into the PCB. So, when we go to the tools, and then go to update PCB from schematic. This dialog box will open. It will list all the symbols what we are using in the schematic. We are seeing here, this is processing the symbol this, processing symbol this, processing symbol this, and then adding the footprint for each of them. This is the add function where we are adding the footprint for all these three symbols used in the schematic. Once we click on this button PCB, update PCB, this is going to convert my schematic into the PCB where I have the footprint from all the devices I am using in the schematic. So these are all the devices. For example, here we can see this is the footprint for battery. This is the footprint for LED. We can see we have used a red LED. So this is the footprint for red LED, and this is nothing but a resistance. We can see this by this R1. This is our resistance. Once we are importing our footprints into this PCB sheet, we are importing PCB footprint as well as the connection information in between these symbols. For example, the battery terminal, this terminal 1 is connected to resistance terminal 1 here. These are two terminals of resistance, these are two terminals of battery. So we see a line going there from terminal 1 to terminal 1 of resistance. This line tells us that there is a connection need to be made from the terminal 1 of battery to terminal 1 of resistance. However, this connection is not made yet. This line is just for our information that this routing need to be done by us to make it a PCB. These are sometimes called rat's nest. So these rat's nests are just the information that these should be connected. However, these are not yet connected. So here we can see this line is from here to here, this line is from here to here. It means this terminal should be connected to this and this terminal should be connected to this. So this is the information we already have now. Once we bring all the footprints together, now we approximately know how much is going to be the size of our board, the PCB, what actually we want to fabricate. So we have this much big footprint, we have this much big footprint and this much big. So based on that, I can guess that this should be our reasonable size of PCB, where I can put all the footprints together and make the connection. So the next step now is drawing a board outline. This board outline is nothing but we are telling the software once we are done, we want only that portion of PCB need to be fabricated, and that when the actual PCB will come, that should be the actual width and length of the fabricated PCB. So we go to the layer and we see this option edge cuts. This option is used to draw the boundary of board and we can have in fact so many shapes. It need not to be a square or rectangle PCB, it can be a circular PCB in some particular applications or some other shapes. So we need to click edge, we click on edge cuts in the layers tab, and draw the PCB boundary. There are many shapes available. You can use a square shaped PCB, or it can be a rectangle PCB, it can be a circular PCB, or we can in fact draw special shapes, for example the circular one, and then we can have different type of shapes available. So there are many shapes available. Can be designed. Once we design or we draw the boundary, in this case we have used only the rectangular boundary. Our final fabricated PCB will have this much of length and this much of width, so that we can measure here, and our actual PCB will be matching these length and width. Now is the time to place the footprints. So the imported footprints, first they were like in random fashion, now we need to take them apart and place them uniformly. For example, this LED earlier were somewhere here. We want to place it in such a way that rat nest, these wires, these wiring information, we try to place footprints such a way that less number of these rat nets are overlapping each other. So for example, we do not want to have so many rat nests crossing each other, because later on we need to replace these rat nests using copper wires if they are overlapping to each other. That time we need to put a via to bring it to the other layer, otherwise two wires will be getting short together. So that time we need to put a via to prevent that misconnection. So the number of crossings we have of this rat nest, the number of vias will be equal to that, and we want to have lesser number of vias, as less as possible, because they increase the complication in PCB design. So in this step we need to place the footprints. So while placing them together, we generally have a line which is containing all the components related to that symbol. For example, here if we see this blue line, whatever pad or silk layer or any device related parameters or layer information that is contained by this blue line. This is called courtyard sometime. This layer is used to keep away other components from this component so that there is no overlapping of two components with each other. This component, which is LED, has this courtyard, and we should not put this battery and LED so close that these layers are overlapping each other. So these are something called courtyard, which need to be not overlapping to each other among these components. So we place all these footprints in such a way no courtyard of one element is overlapping to another courtyard. So almost all components have a courtyard these courtyards should not intersect. Can be two courtyards for a single element if that need to be placed on both the layers. For example, the front layer or the top layer we have different courtyard, and for the bottom layer we have different courtyard. So for example, in top layer this battery everything need to be placed, so we have a big courtyard here. Everything need to be kept away because battery is going to be there in this circular region, and this is going to be the pad, which is GND and VCC. However, if we look from the bottom, these are the only two pins going to be there in the bottom layer. The cell is placed on the top layer. On the bottom layer, that area is free of any element. So on the bottom layer we have courtyard only the small pads, which is this pad and this pad. So for the top and bottom layer courtyards may be different. Now the next step is to wire these rat nests. Now we are doing the routing tracks. So these rat nest, as we see by this line, these are the connection need to be made. So how do we do these connections? We simply click on one terminal and press or activate the layer in which layer we want to connect them. For example, if this is a front layer or the top layer, we go to the layer palette and we choose the FCU, which is front copper layer, and then we connect from here this pad to this pad. It can be straight or it can be with an angle, that depends on us. So we can connect from one terminal to another terminal, and this red line will appear, that is our copper track. The width of this is by default whatever we have specified in design rules 4 slides back. However, here also we have an option of changing it. We just simply click on it and open up its properties. We can increase or decrease the width of this copper line. Otherwise, by default software will take whatever we have specified in the design rules. So this is the copper track we have placed from this pad to this pad, if it is, let's say, 1 mm width, when actual PCB will be fabricated, 1 mm width of copper will be placed on this to make this track. So with the components in place, we connect the pads with copper trace. This we can do by changing the active layer to FCU. So we can change to active layer to FCU, the front copper, and we click on one side of the pad and connect it to the other side. Based on our movement of the cursor, that copper track will be put on the PCB. Next, let's see what will happen if we want to put the connection into the other layer. For example, we want to take up a signal from top layer to the bottom layer. That time we need to have a via in between. So in the routing track itself, now this pad or this element is placed on the top layer. It means this terminal is available only on the top layer, and we want to connect this terminal to the VCC of battery, and this terminal VCC of battery is on the bottom layer. It means this signal or this supply need to be taken from bottom to top. So what we can do, once we click on this pad with FCU as the active layer, we go to here and then we click on this terminal of battery which is in the bottom layer. The KiCad knows that we need to change our active layer from top layer to the bottom layer. So automatically this half wire will come as red, which is the top copper layer or FCU, and half will be shown as blue, which is bottom copper or BCU, which is backside copper, and in between we will have a via, which is nothing but a hole in the PCB going from all the way from top layer to the bottom layer, which is internal from inside. This is all plated by metal so that this signal or supply can go from one layer to another layer. So placement of this via, the software does automatically, and the parameters of this via will be taken from those design rules which we have already set. So here notice that the active layer automatically changed from FCU to BCU. So this is how we connect all the rat nest whatever is available in the schematic or in this PCB. When we import all the footprints, we need to make traces for all the rat nest available. Once we are done with this routing tracks, our PCB is more or less complete. Now we have all the connections available from this battery to this resistance and then to this LED. However, there is one more step which is important to do in all PCB designs and very critical to do in the high speed RF design is placing copper zones. So this copper zones are often used for ground and power connection. Because they provide lower impedance path compared to traces. What does it mean? For example, we have a battery and we want to supply the power to a resistance. Now one option is we provide this connection through this trace which has a width of, let's say, 1 mm, and this is, let's say, 50 mm long. This will have a very significant resistance. This resistance of, let's say, trace is a significant number because the thickness of this trace is very small, 1 mm. it means there will be a resistive drop of this battery, which is, let's say, 5 volts. So this 5 volt whatever we are applying here, by end of this trace this will become 4.99 volt, just because of some resistive drop in the trace. This because this trace is resistive. However, if we fill out the area using copper zones, it means we have a battery which is 5 volt, and now we have so much of area which is filled with copper, whatever is available to us. This whole thing is copper. So effective width of this connection is actually much wider, and the resistance of trace goes down. So when we apply a 5 volt here, typically a 5 volt will appear across the load. So in this way we are transferring the complete signal or power from one place to another without any resistive drop or very less resistive drop. So generally this is the concern with ground and power supply. So wherever we have some space, we want to fill it using copper zones. So there is an option available which is add a filled zone button. We can click on it and draw the boundary across our PCB. So this is the boundary we have made for copper zone. So sometime we do not want this copper on everything, all the area available on the PCB. We just want to define a zone. That time we can edit this zone as per our requirement, but here we are filling the complete PCB. It means wherever the area is available which is not used by the footprints, that will be used by copper. So once we do this boundary and we select fill all zone, so everything within that boundary, wherever we have available space which is not used by any footprint, that will be filled by copper zone. So this is now copper filled, shown by this blue color. Once we are done with this PCB design, the next step is to design rule check. Or DRC we call in short. So for every PCB, when we make this PCB, we run a DRC check. This is a common set of rules which are available in the software, which inspect if for any violation of design rule checking. For example, if we place two components very close to each other so that some layers are overlapping, this can be detected by this DRC. So we can run this DRC by going to inspect and then design rule checker. So if there is any error in the PCB, that will be shown here. For example, this is a error of random PCB and we can see some of the error. If we click on it, this will point us to the location of error in the PCB sheet. So we do this DRC check by this running DRC, all the errors will be listed here. So we need to pay attention to all the errors. We have, for example, 4 errors here in this design and 0 warning. So we need to carefully check all these errors and solve so that the DRC does not have any error at the end. Once we do it, the last step is to send it for the fabrication. For that we need Gerber files, because all these manufacturers, they accept Gerber files. So we go to the fabrication output. So in fabrication output, when we go, we choose the plot format as Gerber. This is the standard format used across the industry. We select all the layers, whatever the layers we have used in our design, we need to select all those layers and plot or save that in a output directory. This is the output directory where we want to save all these files. So this is going to generate more than one file. For example, the front copper, there will be a separate file. For back copper, it will be a separate file. So as many layers we have in the design, those many files will be generated and all will be put in this output directory. We can specify the name here. Along with all the layers, we also need to generate the drill files. Drill is something, the hole which we punch in the PCB for via or holes. So we need to generate drill file. This is the information of we need to put in the PCB at exactly at that location and what size of hole we need to put in the PCB. So this is the complete process of making a PCB right from the schematic. In the last lecture we discussed how do we make a schematic in the KiCad, and then today we saw that we import this schematic into the PCB sheet where we import all the footprints along with rat nest, which says that these connections need to be made. We arrange our footprints together, we make a complete PCB design width and length, and then we route the rat nest using wires. It can be a front on the or the top layer connection or the bottom, or we can even switch the layer. Whenever we want to switch the layer, we need to use a via. We prefer not to have as many via as possible, but sometimes it is required that we need to have number of vias available in the design, because having vias, it increases the cost of the PCB and the signals will be reflected from those vias if it is a high speed design. As we discussed, these vias or these holes, they create a boundary of impedance mismatch, and whenever we have impedance mismatch, signal is going to be reflected from there. So from that reason, we want to have as less vias as possible. So that is a trade off in between going to a single layer PCB or a multi-layer PCB. So this is the complete step of PCB fabrication. That is all for today. Thank you.